Our topic we chose was electricity, and our question was, how does the power grid work? The importance of electricity is very crucial to everyday life because it powers homes, schools, heating, and many more important utensils that we use in our everyday life. It also is crucial for corporations that require internet access, virtual meetings, and other technological equipment that may be needed for their companies. It also impacts the economy by creating jobs, attracting global investment, and provides the productions of goods and services. This year, we all learned about direct currents. Direct currents are electric currents, the rate at which charges flow past a certain point, flowing in one direction. There is constant voltage, charges in electric energy per coulomb as charges move through parts in a circuit. Direct currents always flow in one direction from a negative pole to a positive pole. Usually, these charges come from a battery in a direct current. Some direct currents may have resistors in the path, which hinders the charge flow because charges collide with the atoms in the resistor. Resistors can be lights or switches or other things that take charge to work on the path of the circuit. There are two types of circuits that are direct currents: series and parallel circuits. A series circuit is a circuit that only has one path for charges to flow, so the current is the same everywhere in the circuit. Even though the current is the same, the total voltage has to be added up by each component rather than having the same total voltage across the whole circuit, as well as the total resistance across the whole circuit. Because the whole series has the same current throughout, if one component goes out, for example a light bulb, all the other ones will go out as well. Parallel circuits, on the other hand, are circuits that have multiple pathways for a charge flow with one resistor per branch. The difference between this and a series circuit is that there are one total direct current coming from the source and splits up at each junction, so you lose current at every branch. The total current splits inversely to the branch's resistance, so the more resistors, the less current through each branch. However, unlike series circuits, the voltage across each branch is the same throughout the whole circuit. Each new branch resistor decreases the overall resistance of the circuit. The way you can calculate each of these variables, which are current, voltage, and resistance, in any direct current circuit is by Ohm's law. Ohm's law states that the current in a circuit depends on voltage and resistance. This equation shows that current is directly proportional to voltage. So as a current increases, so does the voltage. Say voltage doubles, so will the current. As current halves, so will voltage. But say current increases, the resistance will decrease because they are inversely proportional. So if the resistance is halved, current is doubled. If resistance is doubled, the current is halved. Ohm's law is important because it allows engineers or electricians to predict circuit behavior or diagnose a problem in the circuits, design the circuits, and or predict what each of the variables will be. We see these direct currents every day in our lives. Like the lights in your room, when we flip a switch, charges flow from a battery source or energy source and flows to each light in the room. It's used in our everyday appliances like our fridges, microwaves, ovens, and TVs. A direct current is flowing charge from a power source directly into and through the object, which is a resistor and flows back out. Without direct current, we wouldn't be able to have electricity flow through things in our everyday lives. An alternating current is a current which switches directions periodically because of a coil that rotates in a magnetic field, which also makes the magnetic flux switch and therefore changes the direction of flow. A magnetic flux is a component of the magnetic field passing through a specific surface. The coil is key in an alternating current because it is a wire in a series of loops or twists that can create or respond to magnetic fields when an electric current flows through them. An alternating current also produces a sine wave, which is different from a direct current because the voltage starts off at zero, then reaches a max voltage. Then, when the current switches directions, the voltage goes back down to zero and eventually a minimum value, and repeats this process over and over. Faraday's law explains how electricity can be created from magnetism. When the magnetic field around a coil changes, it induces voltage, or electromagnetic force, which then causes current to flow. This formula explains how voltage is generated by changing magnetic fields. This formula is important for electricity because it explains how the magnet inside of the coils in a wire generates electricity by the change in magnetic flux, as well as explaining how electricity and magnetism are connected. The relationship between E, which is electromotive force, and N, number of turns in a coil, is a direct relationship because if the number of coils gets multiplied by a certain number, the voltage will also get multiplied by that same number. For example, if N doubles, E will also double. An AC generator is a machine that transforms mechanical energy to electrical energy. They work on the principle of Faraday's law, which states that electromotive force, or voltage, is generated in a current carrying conductor that cuts a uniform magnetic field. This can be achieved by rotating a coil in a static magnetic field or rotating the magnetic field around a stationary conductor. This changes the direction of the charges and also causes the charge to be constantly moving. This is considered as electromagnetic induction, also known as Faraday's law. In power plants, AC generators produce electricity by spinning coils of a wire through magnetic fields, converting mechanical energy into alternating current. This electricity is then sent to the power grid, a vast network of high voltage transmission lines that carry power efficiently over long distances. From the grid, power reaches local substations where it's stepped down and distributed to homes and buildings. Once inside, the alternating current flows through wiring to outlets and devices. Many of these devices convert the alternating current into direct current internally, allowing them to run smoothly and safely.